Yeah, all right. So welcome back to the afternoon session. So our next speaker, so where are your slides?
Right here.
Yeah, okay. Yeah, so our next speaker is Scott Evans. We'll be talking about minimum description length for deep learning. Yeah, thank you.
Great, thanks. And that was great to see the picture there. Sorry I wasn't able to be there in person this time, but looks like you guys are having a great symposium. Yeah, so this talk is kind of following up on the talk that I gave 3 years ago, actually, and really kind of digging into minimum description length deep learning a bit. So um, last time I kind of introduced this idea of the entropy economy, and so I'd like to kind of talk a little bit about that background and motivation, talk about some of my recent work on algorithms. I'm sorry, I'm just going to let my dog out here so he doesn't disrupt. And then I'm going to talk about the Kolmogorov structure function and the variance bias trade, which I think is really formally dealt with, I think, by minimum description length. Okay, here we go. So just to kind of recap. So, my motivation in looking at this, so I work for GE Vernova. We're an energy company, but I'm also an adjunct at SUNY Albany. I teach data science and machine learning and information theory. And I love this quote from the late, great David McKay, who talks about how information theory and machine learning are basically two sides of the same coin. And when we're talking about minimizing energy, we're really talking about entropy and algorithmic information theory and Kolmogorov complexity and things like that. And so I just like to think about the equivalence between descriptive length and energy, right? So every bit, Bennett and others have told us that you've got basically log of 2 times the Boltzmann constant joules of energy anytime you erase a bit. And so when we're compressing everything down into its smallest descriptive length, we're really dealing in the energy domain as well. And so the challenge is that compute is taking up so much of our energy. We're all aware of how the data centers are consuming more and more. AI is essentially an energy problem. We're projected to increase the amount of energy by on the scale of countries, as we move forward. This is throughout the world, huge demands. And I think this is an example I might have used last time, but I take it back to just a simple anecdote from my own life. So my daughter Abby here, she had this bunny, Nikki the bunny, and we kept her inside the garage in upstate New York in the winter so she wouldn't freeze to death. And then I put in a 1500-watt heater to keep her from freezing, and it just killed me because it was a uninsulated garage just throwing energy away. And so I went online and I got a Bitcoin miner for about $400 and heated the bunny with the mining Bitcoin, and it paid for the bunny's livelihood, and it also paid for a semester of college. So if if we can kind of think of things in this way of doing more things, just not thinking of energy and learning as separate things that are optimized separately, but rather part of the same equation, right? And so some of the recent work we've done has been looking at that. And so we're looking at optimizing what, where, when, and how we do our machine learning. And you can, how much better, right? If instead of the Bitcoin mining, I was doing, large language model inference on a GPU, right? Or how much better if I could turn that on and off to stabilize the grid, or take advantage of when my solar panels were operating and not when we were drawing carbon intensive energy from the grid. So so we can look at doing better things with our algorithms, but also where and when distributed data centers is kind of an area I'm focusing on recently. But then how we do it, so that's where the minimum description length deep networks comes in, and so I'll touch on that aspect in a bit. Um, so a recent paper that we just put out was this in the IEEE Sustainable Technologies Conference, really just shows how we can, minimize carbon footprint, minimize energy costs overall by using distributed rather than centralized data centers. The trend is to these huge data centers, and they are, um, you know, working, they're starting up nuclear power plants and things like that to make these things powered. But if we can kind of bring the AI to where the energy is, we can totally transform the um, the problem, right? So we kind of have this idea of, instead of having spinning demand of nuclear power plants or gas power plants or something just there at the ready to provide the energy you need, have a spinning demand of AI jobs that are at the ready to be able to do productive work when you have carbon-free energy available. Right. So the whole idea is that the cost of the energy, the cost of the compute, and the cost of the grid, if you optimize them jointly, you can have new bounds and optimizations. And so, the simple simulation we did was comparing a single data center against, and bringing that energy to that data center from, say, wind farms and solar farms, to having distributed data centers. And basically, the more distributed you get, the less curtailment you have of carbon-free energy, the lower the cost of levelized cost of energy, the lower the need for a spinning reserve. So in terms of you know, meeting the challenges that we face, distributed data centers, I think, is a great opportunity to optimize the where and when we do our AI. But the how we do AI, I think, is also a huge opportunity, right? And so last time in the paper that followed, we talked about how the Kolmogorov structure function really gives us kind of a formula for doing AI in an energy efficient way, right? So today, the deep networks that we have basically overtrain on purpose, right? So if you think about the Kolmogorov structure function, right? So on this axis, you have any bits are in your model, basically, essentially a measure of the complexity of your model. And basically, I'm sorry, this is like the complexity of the models on the x-axis here. On the y-axis is basically the size of your set, right? And so if you start with a small complexity model, you're basically pointing to something in a huge set. And as you kind of use bits to constrain the size of your model, which is akin to kind of increasing the complexity of your data set, you basically drive down the cost of that two-part code until you hit the Kolmogorov minimum sufficient statistic, right? Which is just kind of a beautiful thing. And what I'm arguing is that that is essentially the variance bias trade that we all strive for in machine learning, right? And if you go on from there, you're overfitting, and you can fit your data set, your training data, but you're not really going to be generalizing very well. But the thing about all this is that the energy cost increases, right? So if you're doing a search of every possible overfit model you could have, you're wasting all this energy. Whereas if you can kind of approach it from the left, then you have the opportunity to not waste that energy. And we got some pushback on this because people say, well, wait a second, this Occam's razor stuff doesn't really work with deep networks because we can just train these things and they get better and better. And how is that even true, right? So to kind of take a step back, so there has been some recent work that has kind of validated that. So I really like some of this work. I don't know if any of these people are here, but I think they're doing great work. This predictive coding aspect of, instead of just treating backprop as the holy grail and the way everything has to be learned, using predictive coding gives you a chance to learn at a local level, and gives a great opportunity to scale and do things like that. And there's some other papers that really looked at the description length of deep learning models, and basically show that, yeah, you are actually compressing the data set, even though you have these huge models trained on huge amounts of data. So this work is continuing, and I think, great stuff, and I hope to leverage all that. The thing I want to kind of concentrate on here, so some of our recent work has been looking at how we can have minimize the the energy in creating our models by essentially approaching from the left to the sweet spot. So we have our model complexity increasing, and instead of just overfitting and pruning back, thinking about an Occam's razor approach, going from simpler to more complex. And so here's a couple of the papers that basically give energy efficient machine learning techniques that give similar and sometimes even better performance than some of the brute force models that overfit and then prune back. But I want to kind of dig into this idea. I've kind of loosely talked about how the variance bias trade is, I think, exposed by the two-part code and by the Kolmogorov structure function. So just thinking of it in terms of kind of like a Peter Gax's algorithmic statistics paper is something that I really love. So like if you think about Kolmogorov complexity in these two parts, the complexity of the program that will define the typical set to which your data belongs, plus this non-informative term, that's basically the cardinality of the set to basically pick out the piece of data, the object in that typical set, right? So you have this nice two-part code. You can think of it, very simply, if you have a sequence of ones and zeros alternating, right? You could think of that as a member of the typical set of all 128-bit strings. Say there's 128 bits in it. And you would be right? I mean, it is one of those members, and it's an equally likely member. But you look at it from a Kolmogorov complexity sense, and you say there's something special about that string, and that specialness can be brought to bear in the fact that you can easily define a smaller set to which that is a typical element, right? So you could say it's the typical element of equals numbers of ones and zeros, right? And so your model cost has increased. You've added more bits into your model to reduce your data cost, your kind of non-sophisticated part of the two-part code that basically lets you pick that out. And then you could even go further and you say, well, it's the member of those alternating ones and zeros, equal number set, ones and zeros. But now we're going to go to ones and zeros. You could make this longer and define it as the set that starts on one, right? So we have this kind of trait here. The most generalizing model is the one that will define the largest typical set that gives you the smallest two-part code. And so I think that's the goal, and that's the variance bias trade that we want. And just looking at a couple of simple examples, like if you were compressing this string of roses, using a grammar model, you could find a typical set that had certain elements, and then you could create other generative statements that your poke could say. We've kind of looked at this from a biology point of view as well, and kind of have ascribe meaning to the sophistication portion, which is really that typical set that we're trying to create. And it's really a nice generalization goal. But in terms of just like formally putting this out, right? So say we're looking at the variance bias trade as introduced by Gaman and others. You basically you're trying to minimize the mean squared error of your model, your hypothesis of your feature vector X given the data minus the expected value of your actual output given that X, right? So this is Y is your outcome, X is your feature vector. You want to minimize the error, and you could use a different loss function, but let's just use mean squared error. And so then if you break this down, right, you can break this down into these two parts, one that reflects the variance of your model, which is, how your model is, varying when it's trained on slightly different sets of data, right, versus the average model. So if you think of it like if this was you'd say a polynomial model, right, and you had a high order polynomial model, and you train it on slightly different data, you're going to imagine that your model is going to change quite a bit from the average model. Wherever if it's a lower complexity model, a low order polynomial model, then this variance is going to be smaller. And then the bias term is basically the end difference, your accuracy of your model. And so if you kind of map these two terms, right, the The variance is basically tied to this Kolmogorov complexity of defining that typical set. And so if you think about it, the data you're training on it consists of, the typical set being the set of data that has about the same average entropy, right, within some epsilon of the average entropy of the set. So you've got most of the data is going to be typical. So if you're drawing from that, maybe it's just hypothetical data set to train on, you could think of it as bootstrapping from that data set. Yeah, you're going to train a model. If you get something from, it's probably going to be part of the typical set, right? So your model is going to be, if you're training a model on the typical set, it's going to be close to the average model, because if your model is trying to create the program to write that typical set, then it's going to be, this is going to be minimized, right? And so like having that minimization, as well as the second part of the code, the error term minimized, that is the goal. So basically, I think it kind of brings that whole kind of axiom of machine learning that you want to kind of minimize this variance bias trade right into the realm of algorithmic information theory. And I think it's a beautiful thing to kind of keep track of. So where are we going from here? So we've kind of talked about how we minimize the what, where, when, and how. Hopefully society will be doing what problems that are valuable to society, things other than Bitcoin most of the time. Although we did in that paper I mentioned, we actually showed how you could actually do Bitcoin mining along with something like Monte Carlo simulation and save energy by harvesting the random numbers from your hashes and doing a dual use kind of thing. So there are ways of kind of having some middle ground. You could think of, Bitcoin mining as kind of like the least valuable learning problem that we're spending the most energy on. But like hopefully we'll move to more valuable problems, but that the where and when, by distributed, but the how and is what I think algorithmic information theory can really help us do. And going back to what I talked about last time, I think looking in this Kolmogorov learning cycle idea that yes, every bit has this many joules in it, so let's minimize how many bits we're erasing, be efficient about that. But and there's a lot of work that's looked at how the minimum cost of taking a machine learning model and forming a prediction, say. But I think there's a lot to be done in compressing this part of it, the learning part, right? The learning work that we basically sometimes we just kind of look at Kolmogorov complexity and say, oh, here's a Kolmogorov complexity. And I don't care if it's going to take, that's the whole idea, right? In computability, it could take years for us to compute that, and we don't seem to care about that. But I think we should, and I think we can, because if you think of Kolmogorov complexity in terms of how we do our learning, right? If you think of just a brute force search versus a bisection search, right? The program for doing a bisection search is a little bit longer than the code you could write to do a brute force search, but it's a lot better, right? And so that cost is worth it, and that cost could be manifest if you started looking at like the string of your program log file when you were doing all of your work. So I think bridging the gap between the space and time complexity and descriptive complexity, I think, is an area that we could be really beneficial. And I think that in itself optimizes the what, where, when, and how that we do AI. But I'm very interested in any questions you have.